When electrical conduit becomes warm or hot, it indicates a problem that needs addressing promptly. Several potential causes can lead to this issue. One possibility is overcurrent, which occurs when excessive current flows through the cables, causing them to overheat. Poor splices or connections can also generate heat, as loose or improperly made connections create resistance. Damaged cable insulation is another concern. If the insulation is deteriorated or damaged, it can short-circuit the current, leading to arcing and heat. Conduit size plays a role as well. An undersized conduit can restrict airflow around the cables, contributing to heat buildup. A proper conduit installation can also cause problems. If the conduit is not properly installed or secured, it can create friction between the cables and the conduit, generating heat. Incorrect grounding is another potential cause, as improper or missing grounding can result in stray currents flowing through the conduit, causing it to overheat. Inductive loads, commonly found in fluorescent lighting fixtures like metal halide lights, can generate reactive current and contribute to heat buildup. To troubleshoot and resolve the issue of overheating conduit, consider these steps. Firstly, check the current load. Use an ammeter to measure the current draw on each circuit and ensure it is within the rated capacity of the cables and breakers. Secondly, inspect splices and connections. Verify if any splices or connections are loose, corroded, or damaged. Tighten or replace them as needed. Thirdly, check the cable insulation. Look for any signs of nicks, cuts, or insulation damage. Replace damaged cables. Fourthly, ensure proper conduit size. The conduit size should match the number and size of cables running through it. Use a conduit fill calculator to determine the appropriate size. Fifthly, secure the conduit installation. Make sure the conduit is securely fastened and routed without any tight bends or kinks. Sixthly, verify grounding. Use a multimeter to test the grounding connections. Ensure that the conduit and all electrical components are properly grounded. Seventhly, consider inductive loads. Install inductors or power factor correction devices to reduce inductive effects and heat generation from fluorescent lights. Always exercise caution and follow all electrical codes and safety regulations. Do not perform any electrical work without proper training and qualifications. When assessing the current load, refer to the National Electrical Code, specifically Article 310.15 and associated tables, to determine the allowable ampacity of conductors based on their size, insulation type, and the ambient temperature. For example, if you have a 12 American wire gauge copper conductor with THHN insulation in an ambient temperature of 30 degrees Celsius, Table 310.15 B16 might show an allowable ampacity of 30 amps. However, remember to apply directing factors as per 310.15 C if there are more than 3 current-carrying conductors in the conduit or if the ambient temperature is higher. Use an ammeter to measure the actual current flowing through the conductor. If the measured current exceeds the allowable ampacity after applying any necessary directing factors, then overcurrent is likely contributing to the heating issue. The connections need to be inspected as well, and they should be properly tightened using the correct tools and torque specifications. Oxidation or corrosion can increase resistance at connections, leading to heat generation. Clean the conductors and use an antioxidant compound if necessary before making the connection. Terminals should be properly rated for the size and type of conductor being used. Check for any signs of arcing or discoloration at the connection points, which would indicate a loose or corroded connection. When looking at cable insulation, carefully examine the insulation for any signs of physical damage, such as cuts, abrasions, or melting. Pay close attention to areas where the cable may be rubbing against the conduit or other objects. If you find any damaged insulation, the cable needs to be replaced. In some cases, you may need to use a megometer, also known as a megger, to test the insulation resistance of the conductors. This device applies a high voltage direct current to the conductor and measures the leakage current. A low insulation resistance reading indicates that the insulation is compromised and the cable needs replacement. When ensuring proper conduit size, it is essential to use a conduit fill calculator to determine the maximum number of conductors allowed in a particular size of conduit. The National Electrical Code specifies the maximum allowable fill percentages for different types of conduit. For example, for 3 or more conductors, the maximum allowable fill is typically 40%. Use Chapter 9, Table 1 and Table 4 of the National Electrical Code to determine the cross-sectional area of the conductors and the conduit. If the conduit is overfilled, it can restrict airflow and make it difficult to pull conductors, which can damage the insulation. Secure the conduit installation using appropriate supports and fasteners. The National Electrical Code specifies the maximum spacing between conduit supports based on the size and type of conduit. For example, 3/4-inch electrical metallic tubing, or IMT, conduit typically needs to be supported every 10 feet. Ensure that the conduit is properly bonded to ground using appropriate grounding bushings and jumpers. The grounding system must be continuous and provide a low impedance path for fault current to return to the source. Use a multimeter to verify the continuity of the grounding system and to measure the impedance to ground. Regarding inductive loads, metal halide lights and other types of gas discharge lighting can have a low power factor, which means they draw a large amount of reactive current in addition to the real current that performs work. This reactive current does not perform any useful work, but it does contribute to the overall current flow in the circuit, which can lead to increased heating of the conductors and equipment. To correct the power factor, you can install power factor correction capacitors in parallel with the lighting fixtures. These capacitors supply reactive current to the load, which reduces the amount of reactive current that the utility company has to supply. This can improve the efficiency of the electrical system and reduce the heating of the conductors and equipment. When measuring the current in each circuit with an ammeter, use a clamp-on ammeter, also known as a clamp meter. This type of ammeter allows you to measure the current without having to disconnect the conductor. Simply clamp the jaws of the ammeter around the conductor and read the current on the display. When inspecting splices and connections, look for signs of corrosion, oxidation, or loose connections. Use a wire brush or emery cloth to clean corroded connections and apply an antioxidant compound to prevent future corrosion. Make sure to tighten all connections to the proper torque specifications using a torque wrench. When checking cable insulation, use a megameter to test the insulation resistance of the conductors. A typical insulation resistance value for new conductors is 100 megaohms or higher. If the insulation resistance is below 1 megaohm, the insulation is likely compromised and the cable needs to be replaced. When determining the proper conduit size, use a conduit fill calculator to ensure that you are not exceeding the maximum allowable fill percentage. The conduit fill calculator takes into account the size and number of conductors, as well as the type of conduit being used. When securing the conduit installation, use appropriate supports and fasteners to prevent the conduit from moving or vibrating. Make sure that the supports are properly attached to the building structure. When verifying grounding, use a multimeter to measure the resistance between the conduit and the grounding electrode. The resistance should be less than 1 ohm. You can also use an impedance tester to measure the impedance of the grounding system. The impedance should be as low as possible. When considering inductive loads, use a power quality analyzer to measure the power factor of the lighting circuits. A typical power factor for metal halide lights is 0.5 to 0.6. By installing power factor correction capacitors, you can improve the power factor to 0.9 or higher. When selecting power factor correction capacitors, make sure to choose capacitors that are rated for the voltage and frequency of the electrical system. The capacitors should also be protected by fuses or circuit breakers. Always follow all electrical codes and safety regulations when working with electrical equipment. Remember, the information provided here is for informational purposes only and is not a substitute for professional electrical advice. If you are not qualified to perform electrical work, please consult with a licensed electrician. The heat that stops approximately 13 feet from the switch box could be attributed to several factors. Firstly, the increased resistance due to a loose connection or damaged conductor is more pronounced closer to the source of the problem. As you move further away, the heat dissipates along the length of the conductor. Secondly, the conduit itself acts as a heat sink, drawing heat away from the conductors. If the issue is localized, the heat will be more concentrated near the source and decrease as the conduit absorbs and dissipates the heat. Thirdly, natural convection and air movement can also play a role. The air inside the conduit may be warmer near the switch box, but as it moves further away, it mixes with cooler air, reducing the temperature. To further investigate, consider using a thermal imaging camera to identify hotspots along the conduit run. This can help pinpoint the exact location of the heat source. Also, check the connections at the switch box and any junction boxes along the conduit run. Look for loose connections, corrosion, or damaged insulation. Ensure that all connections are tight and properly made. Verify that the conductors are properly sized for the load they are carrying. Overloaded conductors can overheat, especially if they are enclosed in a conduit. Check the voltage at the switch box and at the end of the circuit. A voltage drop can indicate a problem with the conductors or connections. Consider using a higher gauge wire for the circuit to reduce the resistance and voltage drop. Also, ensure that the conduit is properly grounded. A poor ground connection can cause current to flow through the conduit, generating heat. Check the grounding connections at the switch box and at the service panel. Make sure that the grounding conductors are properly sized and connected. Ensure that the conduit is not damaged or corroded. Damage to the conduit can increase its resistance and cause it to overheat. If the conduit is damaged, it should be replaced. The two grounded conductors present in the conduit could be contributing to the heating issue if they are carrying excessive neutral current due to imbalanced loads on the 120/208 volt three-phase system. In a balanced three-phase system, the neutral current should be minimal. However, if the loads on each phase are not equal, the neutral conductor will carry the unbalanced current. This can cause the neutral conductor to overheat, especially if it is not properly sized for the load. To verify this, measure the current on each phase and on the neutral conductor. If the neutral current is significantly higher than what would be expected for a balanced system, then the loads are unbalanced. To correct this, try to balance the loads on each phase. This can be done by moving some of the loads from one phase to another. For example, if one phase is carrying more current than the other two, you can move some of the lights or fans from that phase to one of the other phases. Also, consider using a larger gauge wire for the neutral conductor to reduce its resistance and increase its capacity to carry current. Also check if the conductors are aluminum or copper. Aluminum conductors expand and contract more than copper conductors when heated and cooled. This can cause connections to loosen over time, leading to increased resistance and heat generation. If the conductors are aluminum, make sure that they are properly terminated using connectors that are rated for aluminum conductors. These connectors are typically coated with an antioxidant compound to prevent corrosion. Another potential issue is harmonic distortion. Harmonic distortion is a type of electrical noise that can be generated by electronic devices such as computers, electronic ballasts, and variable frequency drives. Harmonic distortion can cause the current in the neutral conductor to increase, even if the loads on each phase are balanced. This can lead to overheating of the neutral conductor and other equipment. To mitigate harmonic distortion, you can install harmonic filters on the electrical system. Harmonic filters are designed to block the flow of harmonic currents, which can reduce the amount of harmonic distortion in the system.